Welcome back. In this video, I'm going to solve exercises 1 to 5 of chapter 4 about connected topological spaces. First result, we have a sequence, an of connected subsets of a topological space X, such that each element of the sequence meets the subsequent one. So an meets an plus 1. So we can imagine this as a chain, if you like, of connected sets, like disks. Okay, disk 1 meets disk 2, disk 2 meets disk 3, and so on. And so we have to show that the union of all these sets is connected. Okay, so let us first consider the first two elements, A1 and A2. A1 is connected, A2 is connected, and they have a common point. Therefore, the union is connected, okay, by a theorem of the course. And now A3 meets A2. Therefore, it meets A1 union A2. Therefore, A1 union A2 union A3 is connected for the same reason, because A1 union A2, according to the first step, is connected. So, continuing in this way, can prove by induction that any finite union, so union from k to equal 1 to infinity of AK, is connected by induction on N. But we are not almost done, because we want to prove that the whole union is connected. So the easiest thing to do is to reason by contradiction. If the union, the total union, is not connected, then it has a separation BC. Okay, so there are two open sets, disjoint, non-empty, of X, whose union contain union from k equal 1 to n of AK. Now, since the union is connected, the finite union is connected, then we know from a theorem, from a lemma actually, that the union should be either contained in B or in C, and this is an exclusive OR, because B and C are disjoint. Okay, so we can assume actually that the union is contained in B. Okay, and this happens actually if A1 is contained in B. After relabeling the two sets, if A1 is contained in B, then the whole union, the union from k equal 1 to n, is contained as well in B, because it cannot be contained in C. Okay, and therefore, in particular, an is contained in B for every n, since n is arbitrary. So the whole union is contained in B, and this means that C is empty. And this is a contradiction. So this concludes exercise 1. Exercise 2, similar in spirit. We have a topological space X, and now an arbitrary collection A lambda of connected subsets, and another connected subset A that meets every A lambda. We have to show that A union the union of A lambda is connected as well. So we reason by contradiction. If not, then there exists a separation BC of A union of A lambda. And now, as before, since A is connected, then either A is contained in B or A is contained in C, and after relabeling the two sets, we can assume that A is contained in B. So because B and C play the same role. So, and now the same argument for every lambda, either A lambda is in B or A lambda is in C. Okay, but we want to prove that A lambda is in B for all lambda in this case, because if A lambda is contained in C for some lambda, call it mu, then the intersection of A and mu will be contained in B and C, the intersection of B and C, which is empty, but A intersects A mu, so it's a contradiction. Therefore, all A lambda are contained in B. Okay, so A and the union of A lambda is contained in B, and therefore C is empty, and this is a contradiction. So A union, the union of A lambda, is connected. Third exercise, we have a topological space X and a subset A of X. Okay, so you can draw a figure in the plane. So consider, for example, some kind of disk A, and we have a connected set of X that meets both A and the complement of A. So imagine a kind of arc or something like that, connecting A and a point in A and the point in the complement of A. If you draw this figure, you will convince yourself that C must meet the boundary of A. Okay. And this is indeed the case. So we reason by contradiction. We can write C as a disjoint union of C intersected with A and C intersected with the complement of A. This is the symbol for disjoint union, which is often used these days. Okay. So of course, the two sets are disjoint because A cannot meet its complement. Now, as we know, A is contained in A bar, and we can write A bar as the union of A circle and the boundary of A. And this is also a disjoint union, but doesn't matter here. Because by definition, the boundary is A bar without A circle. So we can write A bar as A circle union the boundary. Therefore, when I intersect C with A, I get that C intersected with A is contained in the union of C intersected with A circle, union C intersected with the boundary. So if C does not meet the boundary, then this is empty, and so C intersected with A is contained in C intersected with the interior of A. But since A circle is contained in A, then we have equality actually. Okay, so C intersected with A is equal exactly to C intersected with the interior of A, and this is not empty. Now, here in this discussion, A and the complement of A play the same role, and they have the same boundary. Okay, so this same reasoning actually, if we replace A by its complement, we see that C intersected with the complement of A is the same as C intersected with the interior of the complement of A. Okay, and this is not empty and actually open. So C intersected with the interior of A is, if you look at this diagram here, so C intersected with A is now open in C. Okay, because it's the intersection of C and an open subset of A. It's an open subset of X actually. Okay, so if you look at this disjoint union, this is open not empty in C, this is open not empty in C. Therefore, we have a separation of C. And this contradicts the connectedness of C. Okay? Therefore, we have to conclude that C meets the boundary. Okay, fourth exercise. We always ask such questions in the exam. So first question, show that no two of the spaces 01 open, 01 semi-open, and 01 closed as intervals of R are homeomorphic. And hence, what happens if we remove 1 point or 2 points or something from each of these spaces? Okay. Second question is about Rn and R. Third question is about the shapes for every, and they exist, or if you like, A and E, because the letters or the shapes A and E are the same. Okay, so let us tackle the first question. First way, how to distinguish between, for example, this space 01 open and 01 closed. Of course, usually students tend to say, well, this is closed, this is open, so they cannot be homeomorphic. Okay, this is not a valid argument, because openness and closedness is not a topological property. Okay, so every space is open and closed in itself. Okay, but we can find a property, a topological property satisfied by 01 closed, which is not satisfied by 01 open. And this trivial property is the compactness. The closed interval 01 is compact, whereas 01 open or 01 semi-open are not compact, so they cannot be homeomorphic. Okay, this is one way of solving the problem. Another way is to use a connectedness argument. So if we remove the point 1 from the closed interval 01, we get what? We get 01 closed at 0, open at 1. So it's still connected. However, if we remove any point from the open interval 01, okay, the resulting space has two connected components, the disjoint union of two intervals. For example, 0A open, A1 open. Okay, therefore, if there was a homeomorphism between 01 open and 01, between 01 closed and 01 open, then when we remove a point, the two resulting space should be homeomorphic, but they are not, because one is connected, the other is not. We did something similar in the lectures. Okay, and now if we want to compare 01 closed and 01 semi-open, removing 1 point is not enough So we have to remove, for example, 2 points. What happens if you remove 2 points from 0, 1 closed? We get 0, 1 open, so it's still connected. However, if we remove 2 points from 0, 1 semi-open at 0, open, closed at 1, then we get at least 2 connected components. It depends which points we remove. We don't know. Okay? If you remove 1, we get 1. So, for example, if you remove 1 and the point A is strictly between 0 and 1, we get 2 connected components. If you, for example, remove 1/2 and 1/3, then we get 3 connected components. Okay? But in both cases, the resulting space, after removing 2 points from 0, 1 semi-closed, is not connected. Okay? Therefore, the original spaces cannot be homeomorphic. Okay, now let us compare, or let us distinguish between 0, 1 open and 0, 1 semi-open. If we remove 1 from 0, 1 closed at 1, then the resulting space is connected. However, if we remove any point from the open interval 0, 1, the resulting space has 2 connected components, so it's not connected. Okay, therefore, these two are not homeomorphic neither. Okay. So this means that we cannot find a bicontinuous deformation that takes any one of these two into the other. Okay, so this is question A. Question B, if we remove 1 point from Rn, if n is strictly bigger than 1, then this is what we call the punctured space. If we remove the punctured space for n bigger than 1, is, as we know from the lectures, path connected, and so in particular connected. However, if we remove 1 point from R, the resulting space is not connected. It has 2 connected components. Therefore, Rn and R cannot be homeomorphic. Okay, same argument for the third question. If we remove the central point in this shape, there exists, or E if you like, same thing. Because E and there exists are just mirror images of each other. The central point is the point where the 3 lines meet. So if we remove this middle point, we get 3 connected components. However, if we remove 1 point from A, or for every this shape, then we may have 2 connected components or 1 connected. It depends which point do you remove. Okay. If you remove this point joining 3 edges, then we get 2 connected components. And if you remove, for example, the vertex of A, of this for all, then the resulting space is still connected. So therefore, these 2 shapes cannot be homeomorphic. Okay, we can also say that the shape for all, or A, has a topological circle, contains a topological circle, whereas E, or there exists, does not contain any topological circle, so they cannot be homeomorphic. This is also a valid argument. Okay, last exercise. We have a continuous function from the unit circle into R. We have to show that f takes the same value at some point. So for some point x, f of x equal f of minus x. What is the... So x and minus x are called antipodal points. Okay, they are symmetric with respect to the origin. So what is the interpretation of, how can we understand this result? If we think of f as being the temperature that depends on the location, so the temperature at each point on the circle. If we assume that this temperature varies continuously in function of the location, then the result states that there exist 2 antipodal points that have the same temperature. Okay, this is the interpretation. And now the proof is easy actually, because we can introduce a new function, an auxiliary function g, which is defined by g of x equal f of x minus f of minus x. Okay, now then g is an odd function in the sense that g of minus x equal minus g of x. Okay, if we flip x and minus x, we get the opposite result. Now, if it happens that g is identically 0, in this case, f of x is even by definition. There's nothing to prove. Okay, so all points are, So therefore, we assume that g is not identically 0, and therefore there exists a point A in the circle such that g of A is not 0. Now we can assume that g of A is positive, because if g of A is negative, so either g of A positive or g of A negative, If g of a negative is negative, then g of minus a, which is the opposite of g of a, will be positive. So there's always a point at which g is positive. Okay, and therefore, by the intermediate value theorem, since 0 is always between g of minus a and g of a, then g vanishes at some point b. Okay, this is the intermediate value theorem, but applied actually not to an interval of R, but to a connected set S1. Okay, so therefore G vanishes at some point B, and therefore in this case f of B equal f of minus B, and we are done. Okay, so this concludes the first video. In the next video, I'm going to solve the remaining exercises of chapter 4. So thank you for your attention and see you next time.